Good morning, everyone. My name is Ryan Bergman, and I'm a program specialist in the Department of Agricultural and Biosystems Engineering here at Iowa State University. Today I'm here with you, and we're going to talk about some spray nozzle technologies, and we're going to go through some updates that have been happening across some of these and talk about future technology platforms that we may be seeing soon come into the marketplace. Brief overview of what I'm going to talk through today. So we're going to focus a lot on PWM or pulse width modulated sprayer nozzles. We'll start with kind of doing a brief overview of those systems. We'll talk through some of the benefits as well as some of the drawbacks of those types of systems. We'll talk through a little bit on sizing nozzles for these systems. That's done a little bit differently. And finally, we'll wrap up with talking through key steps to take to ensure that we get high quality applications with all of our sprayers, pulse width modulated or PWM controlled nozzles or not. And finally, we'll talk through some future application technologies which are enabled by these PWM nozzles that we're seeing adopted widely today. Today, I don't know that we're going to share a lot that some of you won't already know, but hopefully this will be a good review for those of you that are familiar with PWM nozzles. And those of you that aren't, hopefully you'll learn something new about some of the technology that we're utilizing today on a lot of our sprayers. So PWM nozzles or pulse width modulated nozzles. They're not really a new concept. They've been around for quite some time now. The Capstan introduced some of the first ones years ago, and other companies have since entered this space, and we've also seen some updates to existing products in this space as well. So they've been around for quite a while. We are starting to see some wider adoption of these technologies across more of our sprayers in the agriculture space. A lot of this is driven by more OEMs starting to integrate this technology from the factory, as well as increased support and continuing updates on these that have improved the reliability and robustness of these systems from when we first saw them introduced years ago. So there's three main kind of players in this space. I've got a picture of each of them here. So on the far right, we've got a Capstan nozzle system, and then top we have Raven's system, and then on the bottom left, of course, we have John Deere's ExactApply nozzle system. So all of these function in very similar ways. Each of them have some of their own unique features and benefits. We'll talk through and hit on some of those in today's presentation. So I'm going to spend a minute here and kind of briefly overview these PWM nozzles and really how they work so that we understand what these nozzles are doing on our machines. So one of the key benefits or one of the main reasons why we see folks adopting these is they allow us to maintain our spray pressure as we go through speed changes on our machine. So in conventional spray systems without PWM nozzles, we would have to rely on pressure in order to adjust our nozzle flow rate to compensate for speed changes on the machine. With pulse width modulated nozzles, we're able to adjust that at the nozzle level itself. So in the illustration here, you'll see each cycle is 100 milliseconds. So this nozzle is operating at a frequency of 10 hertz, or pulsing on 10 times a second. The flow rate out of each nozzle is controlled by the duty cycle, or the amount of time that we leave the nozzle open during each pulsing cycle. So you can see the nozzle on the left here is staying open for a shorter amount of time, giving us a lower flow rate than the nozzle on the right, which is staying open for a longer period of time during each one of those cycles that's happening 10 times a second. This provides a lot of benefits in maintaining consistent pressure on our machine, which also enables us to maintain better control over the droplet size that's coming out of our nozzles. This has a lot of benefits than just conventional systems where we have to solely rely on pressure. Pressure is not a great way to really manage nozzle flow rate. This is partially because a 2x increase in speed or doubling our speed actually requires a 4 times increase in the pressure in order to match the increased nozzle flow rate that we need to compensate for that speed. So we talked through this example. They're pulsing at 10 hertz here, operating at a frequency of 10 hertz. Today in the marketplace, we have options that are operating at 10 hertz, 15 hertz, and 30 hertz that are available today. So there's some benefits that come with some of those higher frequency nozzle operations. In addition to maintaining consistent pressure, pulse width modulated nozzles also allow us some other benefits that we're going to talk through here today, including individual nozzle section control, turn compensation, as well as some diagnostic features such as blockage and flow monitoring to alert us when there's problems out on our spray boom. So let's talk a little bit more about pressure and the benefits of having uniform pressure across the field. So this is, we vary pressure constantly with conventional systems today. Our machines are constantly speeding up and slowing down as we spray headlands of a field where there might be obstacles, or as we're turning around at the end of each pass that we make. We're naturally going to have these times of acceleration when we're going from lower speed to higher speed in our field. And with conventional systems, as we go through those, the machine's going to attempt to vary pressure as we go through there to compensate for the changes in flow rate that we need. As we change pressure, of course, we're changing droplet size as well, which isn't necessarily desirable as we have a given droplet size that we're trying to target for most applications. The map on the left here is just a map of as-applied speed in a field. So this is a field that was, this is actually a fertilizer application made with a sprayer. And you can see that the varying speeds in this field. So anywhere from like the low end of 6 miles an hour on some of the headlands to upwards of 15 miles an hour in some of the bulk parts of the field. So then we look at a typical nozzle across the pressure ranges and the corresponding droplet sizes that we get with those, and you can see that in that field, we're likely ranging from some droplets that were in the extra coarse category, so pretty big droplets, down to some that were probably in the medium droplet size category as we get into those higher pressures of 30 to 80 psi or so. So those pressure changes, as we've talked about, induce differences in droplet size, and we can mitigate this with the adoption of pulse width modulated systems, which help us maintain that constant pressure as we go throughout the field. Maintaining a constant pressure also has some other benefits around really just making sure the nozzle's operating within the physical parameters of where we intended it to. So this example here that I'm showing at the right is a 110 degree nozzle. It's marketed as 110 degree, but you can see that at 20 psi, we're really only getting a spray angle of 85 degrees out of that nozzle. And once we get up to like 80 psi, then we're pushing a 125 degree spray angle out of that nozzle. And we really want to we've sized this nozzle to be 110 degree spray angle around that 40 to 50 psi range, where we target a lot of our applications. So again, this affects the distribution of coverage on the ground and isn't usually desirable for most of our spray applications. In addition to the spray pattern distribution on the ground that we just talked about, pressure can also impact other areas of the machine, such as distribution across the boom as well. We've heard for years that we need to maintain pressures of at least 30 to 40 psi just to ensure that we're getting good distribution of our product all the way across our large booms that we're using today in agriculture. And so when we drop down to those low pressures, when we're slowing the machine down with a conventional system, we may not be getting good distribution across the boom, where with these pulse width modulated systems, we're able to maintain the desired pressure and control the flow at the nozzle to ensure that we're still getting good distribution both across the boom and within the spray pattern as we go through the spray application in any field. So I've got a video here. We're going to talk about individual nozzle section control now. The video at the right is showing an actual application that we did a few years ago in a field where we had kind of a headland that we came into at an angle, and you can see as that video played there, individual nozzles turning off on the screen as we came through that. So a typical traditional spray system would have shut off sections of the boom as we came through there, and we would have had to have decided as an operator if we wanted to have each section overlapping or shutting off too soon. Either way, we sort of create a sawtooth pattern of over or under application as we're coming into that headland. Depending on the products that we have, that may or may not be a big deal, but certain products that could damage the crop that we're spraying, or potentially products where not getting good coverage is detrimental to the efficacy, such as some herbicides, we could end up with weed outbreaks in some of those areas if we underapplied or left sawtooth gaps coming into that headland. Uh, Individual nozzle section control can really drive some quick paybacks to some of these systems. So, it's not uncommon for us to hear of folks that are switching from conventional spray systems to these systems, to save 2 to 5% on product in a lot of their fields. I've heard some as high as 15% as you get into really irregular small fields that maybe have a lot of waterways and features in them that traditionally they would have had, that would have induced more overlap with a conventional system. So talking through individual nozzle section control here again, another benefit that we get from this is the ability to not outline waterways. This is another key feature that I've heard that a lot of people really like, is the ability to just drive right through a lot of their waterways and let the section controller, the individual nozzle section control, work off the boundary that you have outlined, to shut off right where it should as you go over that waterway. With individual nozzle control, we really reduce the risk of damaging that waterway at all. And, as we talked about in the previous slide, we don't get those sawtooth type patterns, that we want to avoid, to ensure that we're getting good, high quality applications. It is critical, for this advantage, you do have to have a boundary to work off of. The nozzles have got to know where the waterway is. So having a pre-mapped boundary, is key here, to really getting the full benefits of some of these features. However, with some of the new display technologies out there, a lot of times we can generate the boundary once we spray the field once. So we'd have to outline the field once, but then the monitor could remember that boundary and we could use it on subsequent applications as we spray this field, to avoid all the time that we sink into outlining waterways and such, that can really detract from the overall machine productivity in a lot of these fields. So we've heard of folks gaining quite a bit of efficiency if they have to deal with a lot of waterways or other features that they outline by utilizing these systems and just driving right through some of those features as opposed to having to map around them. Also, the nozzles, as we've talked about, the PWM feature of these nozzles will adjust the flow rate of the nozzle as we slow down to go into that waterway, right? So most of the time we're going to need to slow down to cross those waterways, to ensure that we, don't, mess anything up on the machine, and that we maintain good boom height and application here. And so the nozzles, again, will compensate for that, to make sure that we're getting the right rate even as we slow down to go through these obstacles, and help us eliminate any over or under application. So again, next to the pressure, the ability to maintain consistent pressure as we spray fields, being kind of the number one driver to folks adopting these systems. The individual nozzle section control, I would say, is probably a close number two in terms of reasons why people are deciding to switch to these types of systems because of some of the benefits that this can offer. Another benefit of PWM systems, or pulse width modulated spray systems, is the ability to do turn compensation. So what this is the sprayer drives around an obstacle, right, as we're turning the machine, driving in a curve format with it. We're always going to have one boom that's traveling quite a bit faster than the other. So in this example, we're traveling around a 60-foot radius here, which it might be quite similar to some waterways and other types of features that you might cross in many of our fields. With a traditional system, what happens here is the outside boom is traveling much faster than the inside boom, and this results in over application on the inside of the boom and under application on the outside of the boom. So in this instance here, the target machine speed is around 12 miles an hour. That's what the center of the machine is moving. But that inside tip is really moving about 4 miles an hour, and the outside tip, boom tip, is moving about 20 miles an hour. So the inside, we're seeing about a 3x rate applied there, around 30 gallons an acre in this example. And on the outside, we're only getting about 6 gallons an acre when we should be targeting that 10 gallon per acre rate out there. So in this example, the pulse width modulated nozzles across the machine, because we can control each of them individually and vary flow through each individually, we can actually have the outside nozzle be putting out a higher rate than the inside nozzle, which allows us to compensate for these differing speeds across our large booms that we use today in agriculture. This has a lot of benefits to it around maintaining product efficacy, right? So we know that we don't want to be putting products out there at partial rates that can increase pest resistance development. We want to avoid that, and this also helps ensure that overall we're getting the right amount of product on every acre in our field each time we make an application. This video here is a video that I took with my phone of turn compensation on a little sprayer test stand that our dealer allowed us to borrow. So what you see here is across these three nozzles sort of simulate the outside edge on the left, so the outside boom edge, the middle of the machine in the center, and the inside edge of the boom on the far right side. So imagine this on a 120-foot machine traveling around that curve that we just discussed there. And what you can see here is the left nozzle, right, the one that's on the outside of the boom traveling faster, is completely open, right? We're getting as much flow as we possibly can out of that nozzle due to the increased speed that side of the boom is traveling at. And on the far right side, we're at a much lower duty cycle on that nozzle. We're getting the right or a lesser flow rate out of that nozzle because that side of the boom is traveling slower than the rest of the machine. And so we can use this to compensate and get the correct rate out of each nozzle on the boom, even as we go through some of these turning features that we'll often encounter in our fields. So there are, some drawbacks that I think are important to address with these types of systems. While there are a lot of benefits and many people are making the decision to adopt these for those benefits, it is important to realize that, that there are some drawbacks and these systems may not be right for everyone out there. So first of all, the upfront cost can be significant. So these systems are generally cost tens of thousands of dollars, to retrofit on a machine or get as an option from the factory on a new machine that you might be purchasing. They're complex systems. These are gonna add, a significant amount of wiring to a traditional spraying machine, and as we know, those systems can be prone, to getting damage on spray booms and such, and can cause us, some headaches if not properly cared for and maintained. Additionally, this does add some moving parts as well. So every one of these nozzles, has some moving parts in it that allow us to meter that flow rate out and adjust that duty cycle as we spray with these. And, those can, get plugged up as we've mentioned and, can require some maintenance as well. So they may not be for, for every operation out there. And that's something that every operation needs to weigh the pros and the cons and make a decision if it's right for them. Additionally, there's also some restrictions around the ability to use these with certain nozzles and certain products. So we'll talk through some of that in more detail, but we know that certain products out there specify, that we have to use only a handful of nozzles, in order to, abide by the label on those products, and not all of those nozzles will be compatible with the pulsing features of these nozzles. So we'll talk through that here in the next couple slides. So product and nozzle compatibility. So as we talked about, not every product and nozzle combination is going to work here. So I've got a kind of a brief example here. This is the Enlist 1 label, and I'm showing the options for high pro nozzles here. And so they specify only three high pro nozzles can be used up to a given pressure with this product. Each of these nozzles is an air inducted nozzle. And because they're air inducted, those are generally not recommended to use with pulsing systems. We'll talk about some of the details why that is on the next slide. But we shouldn't use those. We shouldn't pulse nozzles when we're pulse the nozzles when we're using this product in these nozzle combinations. So what we can do, though, we can turn all of these systems out there have the ability to revert back to a conventional spray system. So where we just open up the nozzle and we use it as a traditional system, and we don't get the benefits of the pulsing, but that will allow us to use these nozzles, that don't allow them to be pulsed. I like this illustration here from John Deere, and they show, for this nozzle, all the options that this nozzle is compatible with on their exact apply system. So it's not compatible with the 15 and 30 hertz pulsing, as we've talked about, because it's an air inducted nozzle. However, we can still use this nozzle in a conventional mode where we're not pulsing, or with their system, and this is a little bit unique to to the John Deere product here, is they have the ability to do auto switching or auto select A and B, and so can actually have two nozzles activated at any one time. So we could have a larger nozzle and a smaller nozzle and change between them as we speed up or slow down the machine. Or as we reach max speeds in a field, we can actually turn both of those nozzles on and achieve a much higher flow rate by having them both on at the same time. So again, even though we can't, utilize the benefits that the PWM nozzles provide us with some of these nozzles, nozzle tips, we can, revert the machine back to a conventional mode and still make the application even with a machine that is equipped here just by turning that functionality on or off. So I mentioned that, we can't, in general, air-inducted nozzles are not recommended for use with pulsing systems. And the reason is because of how those nozzles are designed, we can end up with poorer distribution of droplet sizes through those. We can end up with some fairly large drops. And we also may not form the spray pattern as quickly. Remember, we're pulsing these nozzles on and off, and so if a nozzle takes too long to get the spray pattern formed, that could be problematic to ensuring that we get good coverage on the ground and making sure that we're getting a high quality application here. So this example, or this screenshot, is from a video that the Nebraska Pesticide Application Technology Laboratory, or the PAT Laboratory, with Nebraska put out, where they're showing how the differences in nozzle and pattern formation happens with two different nozzles here using a high-speed camera. And I've just taken a screenshot here at what I think is a very, very critical point that we want to pay attention to. So the nozzle on the left is an air-inducted nozzle, and the nozzle on the right is a traditional nozzle. Both of them are 110-degree number 4 nozzle operating at the same parameters. They're both operating at 40 psi and a 50% duty cycle. So they're both being pulsed on and off. They're both at the same point in their duty cycle here. So they both shut off at the same time. And this is what we're seeing as the result of that nozzle shutting down and collapsing that pattern back, in preparation of making the next pulse, in a few milliseconds. What we see on the left here with that air-inducted nozzle, we can see some very large droplets falling out of the nozzle tip here as that nozzle is shutting off. And so this is undesirable, right? Those droplets are out of spec. They're not, what we're desiring out of this application. You'll also notice too that the pattern is a little bit narrower at this point, so we're not sort of maintaining that full crisp spray pattern. And compared to the one on the right, which is shutting off in a much more clean fashion, that's much more desirable for good quality applications in most of our agricultural operations today. I mentioned earlier, I think, that we size nozzles a little bit differently for PWM systems, so we'll talk through that briefly here. If you do switch from a conventional spray system to a PWM system, we do need to think about how we size nozzles a little bit differently and make sure that we're doing this correctly in order to achieve the full benefits that these systems can provide us on our machines. If we take the same machine and retrofit it, to a PWM system and use the same nozzles at the same speeds, we're not going to have any room for that nozzle to adjust its flow up or down, because we're typically going to be operating at sort of the max, flow rate of that nozzle, or 100%, flow rate of that nozzle. So typically it's recommended for pulse width modulated systems that we want to size nozzles for around a 70% duty cycle. That gives us some room to both move up to increase flow out of that nozzle, as well move down to decrease the flow as we adjust speeds throughout the field. We do need to pay attention. We want to avoid getting into situations where our duty cycle drops below 20 or 25%. We'll talk through some reasons why in a minute, but in general, we want to stay out of that range, as we can get into some problems with overall application uniformity then. You might hear a lot of folks will recommend, generally as a good rule of thumb, just use like 1.5 times what your traditional nozzle might be. So if you're using, a number 4 nozzle, you might use a number 6 nozzle, or 1.5 times that for a PWM system. We'll walk through, how to do this in more detail here in a minute. In addition, most of the companies out there, that have product offerings in this space also have some apps and websites to help support you making these decisions for your operations. So the picture, or the example here that I have, is from the John Deere Apply Plus app. And you can see that there's information below where you enter in all the information about your machine and what speed you want to go and what you're applying. But then at the top, you can select between conventional, PWM, or auto mode with their system in terms of how you need to size the nozzle. So conventional would be a non-pulsing system, and that'll give you the right nozzle for that. PWM will give you a nozzle that's about that 70% duty cycle for your application, or the auto mode where they're switching between a front and a rear nozzle will help you pick the two best nozzles, to maximize your ability to maintain pressure across the varying speeds that you're going to have with that setup. So just a brief example to show you kind of what this might look like here. So, in this example, let's say we have a machine traveling at 12 miles an hour, applying, a herbicide with a water carrier at 10 gallons per acre. And we're gonna show a nozzle sizing example here for both a 15 and 20-inch spacing machine. So over on the right, I've got just some very base calculations, but on this machine, we're going to be targeting about 29 gallons per minute is what we need to be pushing out to meet these flow rates. On a 15-inch machine, that's going to come to 0.3 gallons per minute per nozzle. And on a 20-inch machine, that'll be about 0.4 gallons per minute per nozzle. If we were with a traditional, spray nozzle here, this would be relatively easy nozzle sizing, right? 40 PSI would be at a number 3 nozzle, at 40 PSI would be at a number 4 nozzle on the 20-inch setup. But remember, for a pulsing system, we need to have some room to move up or down as we adjust the machine. And so we're going to size for that 70% range, which on a 15 inch is going to be about a number 4 nozzle, and on a 20 inch will be about roughly a number 6 nozzle. These calculations won't always come out perfect, so sometimes you gotta just kind of make a decision and pick one. And because these systems will adjust, being precisely on that 70% is not a must-have, but that's just the general rule of thumb to shoot for as you're sizing nozzles, for your PWM system on your machine. Want to hit briefly on a few new features or new products that have been coming into the pulse width modulated nozzle space that I've seen recently. So the first is just in the last couple months, Raven has announced that they have their Raven Hawkeye II system that they're going to be releasing. So the Raven Hawkeye system has been around for many years now. They now have a second iteration of that they're going to be pushing out that has some additional benefits on top of their standard Raven Hawkeye system. From what I've read on this, some of those benefits include blockage detection functionality, as well as getting higher flow rates and accuracy out of each nozzle on the machine compared to their previous system, which, like I said, has been around for many years and has been a good system in the marketplace. The John Deere ExactApply nozzle has been out for several years now. We're starting to see more and more machines out there equipped with this technology. They have, as we've talked about, throughout this presentation a little bit, but they have some unique features that I think are worth noting here on this slide. First of all, they operate at a slightly higher frequency than some of the other nozzles out there that are typically in the 10 hertz range. The John Deere nozzle is operating at 15 hertz, or in the proper configuration can operate at a 30 hertz pulsing frequency. Also, as we talked about, the John Deere nozzle can have 2 nozzles. Can switch back and forth between 2 nozzles as you go through the field and have speed changes. So they call that the auto select or auto mode functionality here. Then they also have some plug detection features as well to provide you some diagnostics in the cab as you're making applications in your field. So a couple slides ago, we talked about, the importance of making sure that we have good application quality. And I mentioned that we need to avoid low duty cycles or duty cycles below 20%. And we're going to talk through some reasons why that can get us into trouble if we get in that range here. So some key steps here to make sure that we get good quality application is understand the products that we're applying, right? We need to read the labels and understand, what's necessary for this product to perform its best in our field. And then we need to set up the machine right. So this is picking the right nozzle, ensuring that we're operating at the right speed for our nozzle, and then making sure that if we do have a pulse width modulated system that, it's set up correctly to get us at the right duty cycle, for the given speeds and pressures, that we're desiring to run at. The danger that can happen here is with these nozzles turning on and off, several times per second, In certain scenarios, you can end up with skips in a field, right? So that's the illustration at the right here is showing a simulated what could be a skip at in certain conditions. So each one of those different colors of rectangles indicates, a nozzle pulse cycle, right? And then the machine's moving forward, and so you get, in this scenario, they're showing 3 distinct pulse cycles. But what happens here is we didn't get enough overlap with some of those, and we've essentially got a horizontal band or skip here in this example. These are pretty rare to have, with most of these technologies. These are not these are not a widespread problem. But what happens with these that usually causes this type of a problem is a combination of low boom height, a low duty cycle on the machine, and fast speeds. And so the combination there is easily fixed by making sure we size the nozzles right, that we don't achieve those low duty cycles, and also ensuring that we have good boom height control. We should be using some type of boom height control system, make sure we're keeping that boom in the desired window, that meets the nozzles and product that we're applying, to make sure that we give that spray pattern adequate time to spread out and get good coverage on the ground. So just to hit on the importance of boom height again, in this illustration here on the right, I think this really does a good job of showing us just how critical boom height is to the overall spray coverage and distribution on the ground. So on the far left side here, we've got low boom heights, and on the far right side, we've got higher boom heights. You can see here, I've outlined a 110-degree spray angle nozzle, which is fairly common, for a lot of applications, that we're making. And you can see at the low boom heights, we might be in that 20-inch to 30-inch range of coverage on the ground. As we get up to some of the higher boom heights, up around 30 inches, though, that drastically increases to could be over 100 inches of distribution on the ground itself. So it's important to realize just how much a small change in boom height of a couple inches or even say 10 inches in some of these scenarios can have a fairly drastic impact on the overall spray distribution on the ground, and we need to be cognizant of that when we're sizing nozzles for our machine and setting up our machines to run, to ensure that we're doing the best job we can to keep the boom where it should be for that application. I will say a lot of the boom height control systems out there continue to improve. We're seeing new features and products from many of the companies that work in this space, that they're working towards getting better control of the boom. They know that this is a critical next step in advancing spray application technology is getting better boom height control. In the meantime, folks that ask me, how do I improve boom stability or boom height control on my machine? A couple of relatively simple things that I can tell people is, first of all, we need to slow down. If we're running fast and have poor boom height control, slowing down, will certainly help give us better boom stability. The other one is if, depending on what type of crop row spacing you're running in, or maybe you're running in fallow ground, if your machine has the ability to adjust its wheel spacing, tread the machine out or widen the machine stance. And by widening that out, we will naturally get some increased boom stability that comes along with that. So those are a couple easy things that we can do to, get a more stable boom with some of these systems today. So as we kind of wrap up talking about some of the nozzle technology out there, I want to reiterate that technology doesn't solve everything, right? We're still subject to all the stuff that we needed to be cognizant of before pulse width modulated nozzles. All of that still applies, now even with this technology. So, we still need to make sure we're setting up the machine right, that we understand the products we're applying, that we're picking the right nozzles, for that application to ensure that, we're getting the best quality of job that we can. In addition, one commonly overlooked thing that, that we still see today is, people not paying attention to how old their nozzles are, how worn out their nozzles might be. So I like this illustration here that shows, worn out nozzles on the top and new nozzles on the bottom. And then the green bars represent, the relative flow distribution across those couple nozzles that they're showing there. So you can see on the top, we've got a lot of peaks and valleys, and, there's quite a bit of distance there, variability in the flow rate that we're seeing from those worn nozzles versus the new nozzles on the bottom. So we need to still pay attention to some of these core concepts that apply with our conventional sprayers as they still apply even with new spray technology that's out there today. And, still paying attention to these and utilizing the new technology properly, will help ensure that, we maintain high quality applications across all of our fields. It's also important to do regular machine calibration, as I mentioned. One of my new favorite things is the spot-on nozzle calibrator tool. So some of you have probably seen this. We've done some videos with this before as well, where it's relatively easy to go and check the flow rate out of a nozzle using this tool, and drastically streamlines that process compared to what we used to have to do here. It makes it quick to go out and check a few nozzles on every section of the machine throughout the season to make sure that something hasn't changed that's causing us unnecessary variability in our application on our machine as we go through the field. So now I want to transition and talk about some technologies that are enabled by some of these new PWM or pulse width modulated spray nozzles that are out there today. So we're seeing more and more folks talking about, and more companies, starting to, release products in this space around see and spray or targeted spraying. We're really just trying to spray, the weeds or patches of weeds in the field, as opposed to just what most of us are used to, where we're just broadcasting all of our products out over the entire field. You start to think about, as you're driving, your sprayer across the field, and, you might see a weed here and there, but really think about how much extra product you might be putting out there that may or may not be really working for you, that some of this technology is essentially working to help solve. So we've got a couple options that I'm going to talk through. The first is using, UAVs or aerial imagery, to identify and spot spray weeds. Then we have green targeting sensors. And then sort of the final technology that we'll talk about is camera targeting sensors, or cameras that, target individual weeds in a field. This type of concept isn't new, right? We've had, folks working in this space for quite a while, right? The two, screenshots that I have here, show just that people have been innovating ways to go out and selectively target weeds in their fields for years, rather that be, some sort of mechanized movement, or, just hiring a bunch of folks to go out and walk around your field and hand remove weeds from your field. These technologies just sort of provide us a new means to do this sort of weed removal from our fields. It is important, and I want to note that these technologies I'm going to talk about are still utilizing herbicides, to control weeds out there. So we still got to select good herbicides, that have good control on the weeds that we're targeting. If we select ineffective herbicides, we're still going to get poor results, even with some of these technologies that we're going to talk through here. The first technology is, or first option here, is utilizing aerial imagery or UAVs, to identify weedy areas in a field. And so a lot of this is really feasible today. We've seen a lot of changes in the UAV and aerial imagery space, and how those have integrated into the agriculture industry in just the last couple of years. We've gotten much better resolution. We're getting much better capabilities and flight times with these types of machines. And so, this is becoming relatively feasible quickly here to do this. So we can use this technology to identify areas of the field that have weed problems. Then there's a couple ways that we can take care of those. So we could, use the UAV imagery to create essentially a prescription map that we could still go apply with a ground sprayer out in the field to take care of those. Or we could use, a UAV itself that has a spraying capability on it to go out and actually spray those weeds from the drone itself. So there are some drawbacks to each of these. So, using a ground rig with this type of scenario, we're not, may not necessarily be optimized, for that type of system yet. So, we don't have a lot of the path planning capability, to tell the machine, hey, you can skip this pass. There might not be anything to spray here, but you need to spray this pass because there's a bunch of weedy spots. Also, some struggles there is, knowing how much product and stuff you need to load on the machine, to make sure that, you have enough to spray all the patches, but don't end up with a bunch of excess product at the end either. The drone side of it, so we can spray these with a drone today. There's several companies out there that are advertising, spraying capabilities with drones, rather than spraying a whole field in some scenarios, or spraying a whole field with a fleet of drones, or using an individual drone to go out and target specific problem areas of a field. Those have all been demonstrated to be feasible by several companies today. Some drawbacks here with a drone is going to be mostly around productivity and some of the regulation side of this. So, the applying pesticides from a UAV is going to come with additional restrictions on top of just normally operating a UAV in a commercial application here. And then also, these drones aren't capable of carrying big tanks on them. So, we're going to be somewhat limited in terms of productivity compared to a ground rig, that we're used to, where they can cover hundreds of acres in a day, that some of these drones may not be able to do that. We're going to have fleets of drones, to really start to get that level of productivity, out of that type of a system. So the next option here is sensors targeting, green vegetation. So these are seeing sort of increased adoption in many areas of the world. We've heard a lot of folks in Australia using some of these, as well as other parts of the U.S. These are somewhat limited to managing fallow ground typically, because they are going to spray anything that's green. So if it's green, we're going to spray it. So utilizing these in a row crop isn't really feasible at this point, because the nozzle is going to always be triggered on by the presence of a green crop itself. But these can be a critical and effective tool for managing fallow ground, and can help greatly reduce the costs associated with managing weeds in fallow ground, which is much more common in other parts of the United States and in the world than what we typically see here in Iowa. The technology behind these is very similar to some of the nitrogen sensing tools that we talked quite a bit about even 5 years ago. Some of those systems where we had sensors on a machine, rather it be a sprayer or like a side dress bar, that would sense the greenness of the crop essentially, and would then vary the rate of a nitrogen product that we're applying as we go through the field. A lot of these sensors are very similar in the fact that they identify something that's green, and then they'll turn on a corresponding nozzle to spray that green vegetation in a field. Some benefits of this technology compared to some of the others we're talking about is they can work in day or night. So compared to UAVs or the next option we're going to talk about that, have limited ability to work in low light conditions. This type of system, because they're just using a light sensor essentially that's shining down on the ground, they can often get by with spraying at night in some scenarios. Again, I want to hit on boom height is going to be critically important to these systems. So because we're turning on, only a limited number of nozzles over top of what we think is a weed, we need to have the boom in the right position to ensure that the spray coverage out of that nozzle gets to the weed in a quick manner, and that we're getting it, evenly distributed over top of that weed. If we have the boom too high or too low, that could impact our ability to get good coverage in a timely fashion over top of that weed as we're moving throughout the field. The final option that I want to talk through is systems that utilizes cameras to essentially look at the vegetation that's available on the ground and identify if that green vegetation is a weed or part of the crop. So we've seen an increasing number of companies that have been working in this space, both in the United States, in Europe, and other parts of the world. There are companies that are starting to talk about this type of technology being available on their equipment. The additional benefits here is that this allows us to spray weeds in crops. So these systems, are imaging the ground, and then they have a computer generally running some sort of artificial intelligence system in the background and an algorithm, to identify what's crop in a field and what's a weed that we want to spray. So these types of systems, are likely going to be available for wider adoption because we can use them in crop. They're not just isolated to fallow ground applications like the last option we discussed. They'll be more readily applicable to more acres across the world. And again, as we talked about, they're going to be relying on good boom height control here. So you can see in this example picture, just how accurately some of these systems might be able to target individual weeds, and ensuring that the nozzle is, in sort of a precise window above that weed to achieve that level of accuracy is going to be key to these systems' success. So to wrap up here and recap some of the benefits here, so there's a couple ways that we need to think about some of the benefits of these types of technologies. So the first and foremost is, clearly these have the potential to help us reduce herbicide costs on our operation. So by only spraying areas of the field where there's a weed, we can reduce the amount of herbicides we need to cover the same number of acres compared to just broadcasting those herbicides out there. I like this sort of example here that I've seen used a lot in this space is, what you used to buy in like in a tote or a large bulk container, right? You might now just get by with a couple 2.5 gallon jugs of that product, utilizing some of this technology. Any savings on the product side could be, as high as like 90 some percent, or might be down in like the 30% range in, in a weedier type field, or depending on the crop stages and when you're making the application. But even, savings in the 30 to 50% range is still going to drive quite a bit of increased ROI from this type of application, just because our herbicides can be so expensive oftentimes. Another benefit that we see with these is the ability, to add more variety to your herbicide plants. So technology like this might, open up the doors to using different herbicides than what you've typically used. Maybe you'll be able to use a more expensive herbicide because you're not covering as many acres. You can take some of that savings and maybe you want to use that to, invest that into a better herbicide plan across your acres. Improved logistics, because we're not spraying, we're not broadcasting the entire field, we're not going to go through as much physical volume as what we're used to on our machines. So we're going to be able to go longer between fill-ups, which means, those machines can cover more, effectively cover more acres per tank in a day than compared to just broadcasting our pesticides out there. Finally, we, overall, we're going to just improve our environmental stewardship with these. So we're going to be less reliant on some pesticides here. We'll be putting, far less volume out there than what we're typically doing with broadcast options. And so those will provide some benefits to us as well. So in wrapping up here, as I said in the beginning, herbicide efficacy still matters with these technology options that we just talked through. We still have to pick effective herbicides. These technologies aren't going to hit 100% of the weeds, right? Some of these are relying on being able to physically see the weed, right? Or being able to sense the weed. And, so if you can't see the weed, we can't hit the weed with the pesticide that we're applying. So some things to think about. What would your level of effectiveness be on your operation, right? Are you willing to, sacrifice hitting a few weeds now and then in order to drive, a larger herbicide savings or ROI on your operation? Also, how would technologies like this, change how you manage the weeds, right? Does this, impact what herbicides and stuff you might pick for your operation? Those are just a few things that we've been thinking about as we hear more and more about these technologies being adopted in other parts of the world. So that's what I have for you today. So thanks again for listening to me talk through some of the benefits and helping to better understand pulse width modulated nozzles that are out there today, as well as some of the future technology options that those might enable within our spray applications in the agriculture industry.